In example 5.8, we have two functions defined for us, full function definition for f and a full function definition for g. And we are being asked to come up with a new function called f composed with g, or you might call it fog. And that is to be interpreted as f of g of x. And that's what's going to help us to calculate the equation aspect of this new function. After we do the equation, we will then go back and analyze the domain, and then we'll figure out what the domain would need to be for this new function. So starting with f of g of x, I need to begin with g of x, which is represented by 1 over x minus 2. So I'm going to substitute that in, f of 1 over x minus 2. And then I'm supposed to take the 1 over x minus 2, and I'm supposed to substitute that in for the x in f. So this is going to become 2 divided by 1 over x minus 2 plus 3. So what I have here is a fraction within a fraction. We saw this earlier in the section, and we called this a complex fraction. So with the complex fraction, my immediate goal is to get the denominator to be just a single fraction. And right now, it's a fraction plus a whole number. So I'm going to make the whole number look like a fraction. So now it's a fraction plus a fraction. But these fractions are not compatible. They need to have a common denominator. So I'm going to take 3 over 1 and multiply it by x minus 2 over x minus 2. This should get me into a common denominator situation. I'm going to keep the 2 in the numerator. My first fraction is going to stay the same, but my second fraction is now going to be read as 3x minus 6 over x minus 2. So I distribute the 3 to the x minus 2, and then I can combine the numerators together, do a combining of like terms, and that'll get me 3x minus 5 all divided by x minus 2. So it's still a complex fraction because it's still a fraction within a fraction, but it's now in a place where I can keep the numerator, change the division into a multiplication, and then I'll flip the bottom fraction and basically take the reciprocal, x minus 2 over 3x minus 5. So now I have a whole number multiplied by a fraction, and if I think of the whole number as a fraction, then it's just multiplying two fractions. In that case, you multiply across the top, and you multiply across the bottom, and you will end up with, let's see, 2x minus 4 over 3x minus 5. So that ends up being what the equation is going to look like for us on this composition. But we also have to be aware that the domain needs to accompany this for our function definition. So the first step in coming up with your domain is to analyze your new expression, the new equation that you're going to be using. So here I have a denominator of 3x minus 5. So I want to pull that out here to the side, and if I set it not equal to 0, then I would get 3x is not equal to 5, therefore x is not equal to 5/3. So that's one domain restriction based off of the new equation that we wrote. But the composition also requires to look at the original equation that you started, the very first one that you started with. The very first one that we started with is g of x. So let me come up here to g of x, and g of x we can see is 1 divided by x minus 2. So that x minus 2 is going to imply that x is not supposed to be equal to positive 2. So that gives me a second domain restriction that I need to be concerned with. So the function definition, we're going to be naming this function f composed with g, and the domain for this function is going to have 2 and 5/3 removed. So that's going to be represented as negative infinity to 5/3 union 5/3 to 2 union 2 to infinity. And this is going to be what maps to real numbers given by the equation f composed with g of x is equal to 2x minus 4 divided by 3x minus 5. And that gives us our full function definition, which is what we were asked to do. And I'll point out here that even though I didn't write out the domain separately, I wasn't asked to do that, so I didn't feel compelled to do so. I do have the domain. It is represented right here. This is the domain of f composed with g. It's embedded into our function definition here.